Hello, hello, hello. We're going to change pace here, and we are going to take a look at a framing system that Jonathan at FabWorks has come up with, and we're going to work on that a little bit. It's going to be very interesting. Actually, let me get this set up, and then we'll start. All right. So get this shared. You can see the what I'm going to be talking about here on the top left, right there. So this is a sort of snap bit framing system that Jonathan of FabWorks had come up with. And so we're actually going to steal this with his permission and adopt it to into the tinyframe repo. Because I've been meaning to build a metal version essentially. This is going to be the opportunity to do that. I have to figure out how to actually post this. Here we go. All right. Shared. Okay. So this is what we're going to copy. Um, tinyframe, real quick, is essentially a repo in GitHub that enables you to 3D print a modular framing system, which doesn't sound particularly useful. But it's modular, so it's reusable. Whereas a 20, you have to cut to length. And then you end up throwing a bunch of pieces, or you end up storing a bunch of 80/20. It doesn't really work out very well. It's kind of a pain. The reason I like modular and fixed length is because you can keep boxes of this stuff laying around, and whenever you need it, you can design essentially in CAD and just either use what you've got in stock or quickly 3D print it. But the key thing here is that you have fixed lengths, and so these lengths here are dictated by the standard size of a 3D printer bed. And by the way, none of this is load bearing, so this is just for tooling. If you need to hold, say, a machine or parts of a machine in place while you're doing assembly. So for some time now, I've wanted to figure out how to do this using metal, specifically aluminum or stainless. And so what the gents at FabWorks have done is they figured out how to do this by using a press fit, not a press fit, a snap fit mechanism to enable you to snap tubing together. And so I want to do a couple things in this stream. Or actually, I want to do at least one thing, and then we'll create the list of things we're going to have to do to validate this from an engineering standpoint. So the first thing is going to be calculating what the press fit, not the press fit, what the snap fit force press-in is, which they said it was about 7 pounds. Let's call it 10, but we want to calculate that for fixed thicknesses because what this is right now, these lengths are based on the thickness of this material. If you use a thicker gauge tube, you're gonna have to make those cantilevers even longer to get the same press fit force. If you don't, then they're gonna be almost impossible to manipulate. So that is the plan. We're gonna do that. We'll do that in Jupyter, and that way everyone can download and mess with the calcs themselves and actually use the calculations to figure out what they need for their project. So this will be a metal version of tinyframe, and so we'll call it something else. We just have to come up with whatever we're going to do for that. But anyways, for the purpose of the stream, let's figure out how to calculate for a given thickness of tube what the required cantilever length is. And then from there, we'll start to lay out the bare bones of the project. If you're tuning in and wondering what happened to pTumbler, it's still in work. It's still in the works. It's right there. It's in pieces. Um, I am waiting for some more parts to come. So while I wait for those parts, we work on our other projects. Okay, so I've already gone ahead and copied the repo from um, from pTumbler for the analysis because I think we actually did some of this calculating for a snap fit already here. So we're going to copy some of that work. So I'm going to start by just going through um, and just cleaning this up and getting it ready for our analysis for this. Um, is it 7 for new? Yeah, it's 7 for aluminum. This is an aluminum tube frame right now. So steel is going to be roughly 3 times more difficult. So for that exact same tube that you see right there, dimensionally, if you were to make that in steel, it would actually be 3 times that load. So 7 times 3 would be 21 pounds of force, which I still think is manageable, but we should be targeting 15 or 10 or something like that. We'll just set 10 as a goal for now. Um, I'll leave it up to you to know why. I can quickly estimate why that is something you can just figure out off the top of your head. It's essentially Young's modulus in this equation. So the deflection is a factor of is not a factor of, but it factors in Young's modulus here. And if this is 3 times stiffer, or if this is 3 times bigger, then it takes 3 times as much force to get the same displacement. And yeah, you can, if you don't believe me, go look up the Young's modulus for aluminum and then for steel, and you'll see that. Now the good news is steel is much stiffer, but you get a return by factor cubed on your length. So I actually think this is going to work out fairly well. Because you could have a case where if you go to super thick gauge on the tube here, you would need way more length to accommodate that stiffness. But because, like I said, I think you get a factor cube here. It's actually way more palatable than you would initially think. So let's get started on these calcs. But first I'm going to clean up this repo. Tolerances. Technically, hardness does not impact tolerance. Technically. Tolerance and hardness are 2 different things. If you're asking about um, Hertzian contact stress and deflection associated with that for things like pins and slots and holes and so on, again, it goes back to modulus of elasticity. It doesn't really have much to do with hardness. When you get into it, if you want to go into the advanced analysis, there are books that talk about how case hardening, for example, does impact localized yield values, or not yield values, but localized elasticity values. But I haven't dug too deep into that rabbit hole myself personally. I have for projects in the past, specifically around calculating contact stresses for gears. But in this specific case, I don't think any of the materials we're going to be dealing with are case hardened. So you will not really need to care too much about hardness. Okay. Let's get to it. Really want to make a fast and easy way to just quickly copy these repos or this analysis into new repos. all this stays the same. This does too. So this was boilerplate for the system level variable declaration for the tumbler, things like weight and volume and so on. So I don't think we need this. And actually, I should copy this before we keep going. Okay. Okay, so we can delete this. And the reason why I copied that was so that if I make an error here, we can quickly go back and copy that. Don't need that. This chart we do not need. We're really not going to use much of that. Okay, so here's where we actually want to save some of this. So this is where we did the cantilever calculations here. Oh, and I should take a step back and say, why do we care about cantilevers when we're calculating snap fit press force? The reason is because these are essentially just cantilevers here. So I've actually got the CAD, by the way. The gents at FabWorks were kind enough to send this over to me, so thank you to them. So these right here are essentially the cantilevers. And the cool thing about cantilever flexures is you can approximate them as beams. And so that's what we're going to do here. And actually, I'll quickly just take a screenshot of this so we can actually draw on this and talk about it intelligently for the calcs. So get this out of the way. I'm still chuffed that this worked, by the way. You should go watch that stream if you missed it, but we found out that we actually used the determinacy equations to figure out if we had the correct amount of restraint for this bearing assembly. First time I've ever done that, and it actually worked. It's pretty cool. Might actually start doing that from now on for bearings. Okay, so in the beam equations here, inside of essentially what is I here, or second moment of area, are the dimensions of the cantilever, the snap fit beam here. And so I'm going to draw out what those really are. And so this depth here, actually, let me write this out so we can be on the same page. So when you analyze a cantilever, you're going to need something called second moment of area. And in second moment of area is for a rectangular beam like this is BH cubed over 12. And if I'm wrong about that, please correct me, but I've abused this equation enough that I think I've got this right. And so what does that mean? It means I is roughly, if you take a cross section here, my drawing skills are getting worse and worse with the mouse, but you have to live with it. So for AA, it's pretty simple. It looks like this, right? And so H is the thickness, and B is the width. And this is going to help determine the section and how resistant to moment. I'm sorry. Second moment of area does many things. In this specific case, it is going to tell us how much it resists bending moment, which is going to regress back into stiffness for us. So that's the cross section. I'll actually draw out here what these values are. And so this is H, and then this is width, and that is B. And so this is going to be really important, and that is what we're analyzing here when we look at this cantilever beam. Now, why does this matter? Because this tells us for a fixed displacement or force what the snap fits are going to do. So I'm going to delete this because I think it's irrelevant now. This is what we care about here. But we can solve this for P, right? And so that's where this becomes useful. Because we're going to say, hey, we need this to deflect. First, we're going to find how much it deflects for 7 pounds. That's going to give us this fixed displacement. We know that works. The video here shows 7 pounds deflecting this the appropriate amount. So it's actually cool. We can actually, from the fact that they sent us the CAD and they measured and told us the press force, I can actually figure out what the actual deflection of that beam at the tip is based on that information. They don't need to go measure that. I can actually figure that out from these equations. Once we have that distance, we now can say, okay, this needs to deflect, say, 1/4 inch. I know it needs to deflect 1/4 inch for this thickness of tube. If we want to double the gauge on this tube, what is the new force to get that 1/4 inch of deflection? That's one way to approach it. Another one is, okay, well, no, we do have to do that, I think. And then we check to see how much force it also takes. So this will be interesting. How should we solve this? Should we solve for force or do we solve for displacement? Or do we have to solve for both? We really care about, oh no, wait. We have displacement, we have force, then we get the length required of the flexure. That's right. And so these lengths here are going to change. So this is great. So this means now you just put in how thick your tube is, and we spit out how long these cantilevers have to be for you to get the right displacement and the right displacement and force. That's right. So going back here, what I mean by length is the length of these flexures. So the length of the flexure is the start of the cantilever here to the end of the cantilever here. And so this value is L in these equations down here. So now we're going to put this into Python. We're going to make it so that any user can just put these values in and then just use the tube as required for their specific application. And I will, after the stream, go make friends with a front end dev to find a way to slap this into either a GitHub or a page on the project that we can use to actually build a little web calculator for users to figure this out. Or we just go through the combinatorial problem of what thicknesses of tube are actually available and what the values are so people don't have to run the calcs themselves. So we'll figure that out as we go along. First step is let's figure out how much actual length we need depending on the thickness of the material. So we'll get started on the calcs now. We don't need this. This was for FEA, we don't need this. This was for manufacturing. We don't need that. Stress calcs. Actually, that's a good point. We should also do stress calcs here. So I'll make a little to-do up here. So to do, we want to do stress checks for given thickness in the declarations above. Okay, don't need this. Same story. Del, this is for another analysis in eTumbler. And so now this is all the relevant information. Well, all of this is acting elastically, Bender. So I don't think we care about spring back or anything. At least in my mind, it's all going to be elastic. For me, my read on this is that this is the idea, well, for my project, I don't know about their assumptions on this. For tinyframe, the goal has always been reusability. So the idea is when you're done with these tubes right here, you can put them back into, well, yeah, you can put them back into your storage and then reuse them later. Okay, so let's see. So we have the equation for deflection, load, and we declare second moment of area here just for some, well, not for simplicity, but just for the reader. So it's good to have that. Now, we actually want L. So let's solve for L. So here's the equation. We have deflection So we have deflection is equal to PL cubed over 3EI. Now, what we want is to know how long these cantilevers have to be to enable this design for any fixed thickness and change in the second moment of area here. So this is a constant, we're not changing that. E, that's going to be based on the material, so that will change, but that will get declared with essentially like a drop down. Yeah, right, Jonathan? It's a sick tube, bro. Want to give it some love, though, on some stress relieving features. We'll get there. Second moment of area, this is what's going to change in the back end. P is not going to change. I've been told it was 7 pounds of force. They went out to the shop and actually tested that. And then L is where we're going to get this is where we're actually going to get some answers in how long these flexures have to be for a given thickness of the tubing. So now we know we want the length. So let's solve for this length. So right off the bat, we can actually shift the denominator out and pull the pull this one down, and that'll get us to the first step to solving for L. So that's now del times 3, or 3 del E I, because these shift up, over P is equal to L cubed. Let me double check this. 3EI, 3EI, P, P, L cubed, del. We're good. So now we take the cube root of that and we get our answer. So the length of this snap fit is going to have to be the cube root of 3 del E I over the load P. So this is our equation. And so let me copy this into Chat GPT and get the LaTeX for that. This is my favorite use of AI right now. All right, so let's actually copy this into our equations. Actually, I don't want to do this yet. I want to solve for I first. I'm realizing that now. So let's actually break this out into terms of I. Because as I said, we actually want to solve for thickness as well. I think we want to, yeah, let's write this in terms of second moment of area. We should do that. And as I said, I think that's BH cubed over 12, but we'll double check here. Yeah, BH cubed over 12. Okay, so let's solve this out. So L is equal to the cube root of 3 del E, and then we're going to take out BH cubed over 12, which is BH cubed, and that gets over 12 treatment there times P. And so what we've done now is we've said, okay, the width of the flexure and the height of the flexure now are incorporated. And we can solve for these as well. My P looks really sad. So I'm going to fix my P. There we go. So now I'm going to have Chat GPT write this out. All right. Let's see if that looks right. We have 3, yep, cube root 3 E BH cubed over 12P. That's right. And who said AI wasn't useful? Tabs, yes. Lex, you're correct. We'll call them tabs. Ben tabs. I like Ben tabs. Actually, we should P is going to be the total force. And we have 4 tabs. So you see where I'm going with this. All right. So how do we do that? I think we just do P over 4 here. In other words, we're saying there's going to be 4 of these. So essentially, Bryce at FabWorks said, what did he say? He said 7 pounds of force total. So that means each tab had to do 7 over 4, which is roughly 2 pounds. So this gets smaller. Yeah. So this is actually P over 4. And when you do the algebra, that turns into 4 times this. And 4 times 3 is 12. And you see what's happening here. And then 12s cancel out. So we get a pretty beautiful equation with no constants. You truly love to see it. So we're going to get rid of 12 here. I think I just broke that. Let's see. Nope. We do need to delete the 3. Okay. All right, let's make this clear. P is the global press force required. We normalize. Actually, let's leave the initial equation for so that way we can say what we're about to say. Make it clear to the user. And it was, yeah. Okay, and we'll fix this again. Okay, that looks right. Okay. Let's see. We have our equation. Now we can solve for L. Let's actually go through the existing calcs and fix that up. So we have, this is actually going to be, actually let's get rid of the nomenclature delineating exactly what material that's going to be. So I don't think we actually want that. Just normal, we'll actually reword these into, or redeclare these into what they are going to be regardless of material choice. And then again, change that. So actually we don't calculate I here. So, and then actually we now go back here and get our equation that it spit back out for us. So this long string is the answer. Figure out the length. So we should totally reword that. what do we call it? Bend tab? No, actually bend tab isn't right. It's flex tab. Flex tab. Okay. And so then we get our length, and then we want to actually replace this. So it's going to be length, and then we're going to change that to millimeters because we are going to think in terms of metric. Locking tabs. I like locking tabs. Flex is a little ambiguous. Good call. Yeah, and that's going to be broken for now. Okay, so we have 3. We got to get rid of that. And then we're going to get rid of this. So del E BH cubed divided by P. And that's all to the power of 1/3, which is the same as this cube root. So now we have to make sure everything's declared. We have del, we have E, we don't have, yeah, we do have B, and we do have H. Okay. So let's test this out. Let's see if it gives us this length. We can actually see if this equation is correct. It's not going to work because math is made up by intellectuals to trick regular folk into not doing real work, but we might get lucky and this might actually work. Let's see. So let's just double check all these values. So Young's modulus for, what's Young's modulus for? I think it's 20 e to the, we are in PA, so it's going to be 69. Nice. PA. Why did, no, that was steel, that's why. All right, 69 e to the 9. 69 e to the 9. Yep. Is that right? Why is that? Yeah, 70, roughly 70. Okay. Makes sense. Okay. L, we don't have L yet, so we actually delete this. Del, del here is the required deflection. Oh, we need to solve for del first. That's right. We need to solve for del first. Then we can start spitting out what the new lengths are. So, did I save that? Right, we'll just write this out manually. So we need to solve for the deflection first before we can start regressing back into the length. So del is equal to P L cubed over 3 EI. And our I is BH cubed over 12. So BH cubed. And then the 12 comes up here. Because when you divide a denominator, it turns into a, goes up to the top. And then this turns into del is equal to 12 divided by 3 is 4. PL cubed over EBH cubed. Okay, right? Let's double check this. IBH cubed over 12, yep. PL cubed, 3E. 4 because the 12 divides by 3, that's 4, yep. PL cubed stays, yep. BH cubed, we're good. So we'll have ChatGPT do the same thing. So we'll actually start breaking this out into relevant sections. So we don't need load. So we're going to copy this out actually. I'm going to delete this. Okay. Calculate the length of the flexure, yada yada. These come down. Okay. So these are last, and then up here, we're going to solve for delta. Okay. Let's go to ChatGPT. Can you hear crows in the background? It'd be really funny if you can. Yeah, I think you can. I built a crow feeder, and I have crows in my quote unquote yard. They're pretty loud whenever they want more peanuts. That's probably one of the weirdest facts about me, is that I keep crows. I don't actually keep crows, but we're almost friends at this point since I feed them so much. Let's add a cell below. Wish I knew what the keybinds for this stuff were. I think that's right. Okay. All right, so we're solving for del here. We should declare E and all of that up here above these equations. Or actually, we'll do it over here. So we'll just move this stuff. Yeah. So we don't know this yet, so that gets deleted. These we do know. And actually we'll just, or yeah, we do know. And so we'll actually move this to where it needs to be over here. Okay. And so now we also can put in, how do you spell your name, Jonathan? Jonathan? And it's Bryce, right? We know the E value for, the Young's modulus for aluminum. The P was, we said, 7 pounds force. And as I'm typing this out, I'm realizing we made a mistake in these equations. So um, this is again by a factor of 4. Um, so this turns into P over 4. Which turns into just P. So it's just this equation essentially divided by 4. And so 4 over P times 4 is just P. Always use that. So now we solve for this. Okay, so we don't have, so we do have the initial L, and so we'll call that L sub 1. Actually, L sub P, because that was a prototyped. L prototyped. And that's going to be this distance from here to, actually, let's call it here. It's probably more representative. And so that is, what is my delta x here? My delta x is 75 millimeters. Okay. So we have P, we have L, we have Young's modulus, we have B H cubed. Let's actually double check our B value real quick. That's just the distance from here to here. And it's not giving me my value, so let's try again. Oh, it's right there. 6.4177. And the thickness is 1.651. And that is millimeters. And so now we can copy and paste the code, and we can get our answer. And this is going to be del, I think we're calling this del, right? Yeah, del underscore. And we left the 4 in there because we forgot to tell ChatGPT that we made a mistake. And so here's our answer. And of course, that doesn't make sense because we changed this variable name. So now this should work. And we'll print this value out just for sanity check. So this is going to be del sub, and then we're going to convert that to, we want it, actually, let's see what it spits it out as. It should be millimeters. That's not a millimeter. So I love pint, but it's pretty bad at simplification of units. So that goes to ureg.millimeter. All right, so they were getting, do you see the magic of math, everyone? How cool is this? They gave us the CAD and they gave us the press force, and we were able to figure out using 150, maybe 200-year-old equations, what the actual deflection was, and that's super useful because measuring that would have been really tough. And what we're saying here is, let's see if I can pause this. What we're saying here in these equations is when he pressed this in right there, it's hard to see, but right here, that deflected essentially 7 millimeters, um, which looks like it might be more than that, but I'm going to trust him. Yeah, that looks more like 15 millimeters. But I'm going to trust Bryce. So what's that in freedom units? Quarter inch. Um, Pretty cool. Okay. And we'll apply a safety factor to this later, so it's not the end of the world. So let's actually just kind of summarize this real quick. All right. So roughly 7 millimeters. All right, so now we have this value, we can actually come back here and solve for this. We can actually figure out what our required length needs to be. And so if we solve for this L, we should get the same L up here, which is 75. So this is just a good sanity check. Yeah, good point, Jonathan. So you're right, it is actually this distance here from, what is it, from here to here? And that distance is, well, would you look at that, 8 millimeters. Huh. So the math pretty much works. How cool is that? Actually, now that we know that, let's not use the regression and actually um, let's actually rewrite this to say as a function of whatever your tab distance is. Yeah, I know when the math works, it's like the best feeling, but it only works like 5% of the time, so enjoy it while we can. We should actually use this deflection as an input, which is, now that you said that, way more intelligent. But I'm glad we did the check here. Just to make sure that this is all checking out. So the length, okay, so 1 second. You're going to get to meet my dog. You've heard her a bunch. Now you get to see her. Um, okay, so we actually should, well, but I don't want to give the user the option because we really want to define this geometry. So all we're going to do is we're not going to give them the option. We're just going to say, hey, we know that this is actually 8 millimeters. The math checked out here. But we're going to use 8 because we know that from CAD, that's really what it's going to be. And the good thing about that is we can actually adjust this geometry if needed. We can actually say, hey, actually, we can make this a little bit smaller, and we can reduce that force, or we can make it bigger if we really need to, and we can make it, we can increase, I'm not sure what that does exactly. We might be in a case where we need to do that, so let's write that out real quick. Actually, I'll add the cell below this. Oh wait, I want to do it up here. You're not going to get to see my dog. That'll be for another stream. She got a hold of some chicken juice today, so that's been the disaster of the week. She seems to be doing well so far, though. Okay. All right. So Yeah, the tab does look like overkill. It does look a little yellowed. I was thinking about running some FEA to actually get the optimum sort of dimension on some of the stuff, but that's for a later us problem. Right now, let's just make it work, you know? All right, so we got our del. We should tell the user, okay, well, regardless of the solution, we are going to calculate based on a target deflection, not on what was prototyped. Well, del tab. Um, yeah, the the length of the tabs, that's part of the reason for this is having these long ass tabs is kind of a pain for a million reasons why you probably can imagine. So the cool thing though is you can say, okay, well that was 7 pound force installation. Realistically, we actually only need say, let's say like we don't mind the user having to use 50 pounds, which that's a lot, but the upside of saying 50 pounds is you can make the tabs way shorter. Um, but that then gets into the territory of are we actually yielding the material, which is on our to-do list. Okay, so given the analysis matches CAD, blah, blah, blah. Now we need to calculate the length of the flexure. Um, and so what we'll do is we will change this to del tab. So del tab, as we said from CAD, was 8 millimeters. So del tab is 8. So now we have del tab, got that, E got that, B got that, H got that, P got that, 1/3 got that. About to get our answer. And what is it? It's broken. Convert magnitude. So I've messed up my units here. This is why, one of the reasons why I like the Pint library, is it catches you when you make mistakes. So where did we make our mistake? Let's look at our declarations. So del tab millimeters, that makes sense. Yep. Let's actually pull up our equations here just so we can sanity check ourselves. So up here, del E, where's E? Where's E? Pascals, that's right. B, millimeters, H cubed millimeters. P should be pounds force. So why are you breaking? What's going on? Why don't you like this? Let's see what you spit out without the unit correction. Millimeter Pascal force pound. So something went wrong here. I'm willing to bet pint can't handle cube roots. I'm willing to bet that's the problem. And we'll double check this ourselves. So what happens? So actually, let's do the unit analysis on this. Del is it unitless? No, del is in millimeters, I think, or unit length. Yeah, I bet you can ask ChatGPT to just write it in JS for you. If you have it, if you give it the Python, that'd be kind of cool if we could do that. So del, I think is, so yeah, del should be that. I think del is units of length. I don't think it's unitless. Yeah, no, it's got to be length. So that's um, L for units of length. E is, I think it's um, force divided by area, which is length squared. B is length. H is length. Then P. So 1, 2. These cancel out and you get length cubed. Yeah. And then the cube root of that is length. So what's going on? Python is the problem. We are not the problem. So let's double check this. Maybe ChatGPT gave us some garbage code and we have to fix that. Let's see. Del tab is millimeters length. E is Young's modulus, which is area. Not area, it's stress, which is force over area. Just double check the units. Stress over strain. Units of stress, so that is force over area. And did we do that correctly here? Let's see. Oh, PA. Let's just write up pascals. Let's see if that works. Millimeter Pascal, force pound. Is force pound the problem? What's going on here? Did we... Oh, do we... No, we do need del tab. So that's length. Okay, so length, force over area, length, length. Or B and H length, they should be. Yes. Over P, which is P incorrect? No, that's force. So what's going on here? All right, let's just do L temp. See what happens if we get rid of this. I'm really frustrated that I have to be burning time on this instead of doing the actual engineering. I know that we didn't do anything wrong here. Millimeter Pascal force pound. So Pascal divided by, yeah, so this is in units millimeter cubed, which if I now do L temp equals we do the cube root on this, that should return us millimeters. For some reason, it's not recognizing pascals as area, and it's not simplifying to just units of length. Yeah, so this is a Python problem, not an us problem. We're doing this correctly. You hate to see it. All right, pint unit analysis cubed not working. I bet you there's someone on the internet who dealt with this. No wonder no one uses Stack Overflow anymore, because it's filled with pop-ups. Okay, let's see what they say. Since your contacts, blah blah. I think that's us. Pint unit simplification. Sorry, you have to watch this. Two base units. Dot two reduce units? Is that gonna fix this? I think it's dot two reduce units. Let's try that. So two reduce units. No, it did not do it. None. Fantastic. Okay, we're gonna brute force this. Am I proud? No. Should the pint team be proud? I cannot say. They're doing great work. This is free software. I should not complain. So I'm not going to complain. So I'm going to be thankful for the work they've done so far, and I'm going to see if I can help them fix this in the future. Yeah, if you want a primer on why engineering software for mechanical engineers is stuck in the Stone Age, this is an example of it. Because, you know, Pint is the best at this, and it's still barely working. Okay, so what we're going to do is we're going to brute force this by just extracting the magnitude out of this. And then understand that this is most likely in millimeters. So we have millimeter force pounds. I don't like this. Oh, you know what? We can brute force this. So we'll actually change this. I bet you if we change this from force pounds to newtons, this is going to fix itself. And it's 4.4 newtons to pound. So yeah, that's right. 7 times 1.4, roughly 31. So we'll change this to 31 and then newton. See if this works. For an L, we still get Pascal newtons. What if we brute force pascals as pascals or newtons per meter squared, I think. Pascal units. I think it's newtons per meter squared. Yeah, newtons per meter squared. So this turns into 69 e to the 9 ureg times newtons divided by ureg dot meter times ureg dot meter. Are we having fun yet? Yes. Yes. All right, so we tricked the software into doing what it needs to do. So the length of the flexure has to be 80 millimeters. So 80 divided by 25.4. So roughly 3 inches of flexure here is required in freedom units. So, and I bet if we read this again, yeah, that's right, it was 75 before, 80 roughly the same. So everything's checking out. This is great. So now we have the length. To do was required deflection. This is done. What's the markdown for calculating? I mean, what's the markdown for a strike through? Curious. Nice, there is. Look at us. Pretty much software engineers now. Okay. Build calculations for unknown press force, also done. We need to do stress checks. This one should be easier. So stress, given everything we know here, bending stress. So I'll just do the quick rundown of what stress we're going to calculate. So we are bending this tab down 8 millimeters. Ooh, that doesn't work. Okay. I wonder if this works. No. Let's see. No, that doesn't work. Okay. So we're going to bend this tab down 8 millimeters. So the only stress we're going to see here, well, not the only. Technically, you're going to see 2 stresses. I'll draw it on this one. So you're going to see 2 stresses. Essentially, you apply load P here, right? And then this is going to bend down. That stress is going to be, essentially, you're going to get bending stress at the outer and innermost fibers. I'm sorry, that. No, only at the outermost fibers on the outside of the tab. And technically, you will also see an additional shear stress here, but we can ignore that for now. And the reason why you can ignore shear stress is long-winded, and it has to deal with how shear stress distribution goes through a member. And I will talk about that at some point, but right now I just want to get to an answer here because we're running tight on time. And so what is that stress going to be? The stress is very simple. It is normal bending stress is equal to MC over I. It's that simple. So let's get ChatGPT to write this out for us. If you really want to know why shear doesn't matter here, just let me know. Maybe I can do another talk about that, but okay. Why did that explode? So let's declare yield stress. Um, so sigma yield for aluminum, I think they're using, let's assume they're using 5052. I'm sure they were using 6061. But just to be conservative, we'll assume 5052. Is 28 KSI. Um, the distance to the outermost fiber, this one's easy. C is equal to H divided by 2. So it's that height from before, but it's the distance from the centroid to the outermost fiber, which is just the thickness divided by 2. And then I is going to be E H cubed divided by 12, as we said before. And so now we get our answer, which is sigma B is equal to, oh, the moment. That's right. We got to calculate moment. So moment is equal to the force, which is P, times the length of the flexure, which was L. It's that easy. So then we get M times C divided by I. And we should get an answer here. Gave it to us in Pascal, so we'll get that back in KSI because I think in terms of freedom units. That's a lot of stress. So they're permanently yielding this. So, yeah, I mean, so the factor of safety, I mean, yeah, is that right? Technically, they were permanently yielding this on the prototype. It doesn't look like they were. Well, actually, they might have been. Actually, yeah, you can kind of see it. Is there a way to make this bigger? There isn't. Darn. So that's not good. So these tabs actually have to be longer, this is saying. Is that right? I mean, they snap back up, but you can kind of see a gap there. But it's hard to tell if that's from interference or if that's from yielding. I'm surprised by that. I'm really surprised by that. So what is our factor of safety here? We want 1 at least, but we're way below 1 right now. So factor of safety. Oh, it's because we assumed 50-52. Even then, that's still way too high. That's 100 kip. I mean, 100 KSI is super high. It's like really skookum steel doesn't even do 123 kips typically. So our factor of safety is going to be sigma bending, sorry, sigma yield. Yeah, sigma yield over sigma, the actual yield stress. I mean, the actual stress it's seeing. So 0.22, we're roughly 4 times under what the acceptable yield stress is. I happen to know that 6061 is 42 KSI. Am I doing something wrong here? Is it so MC over I? That's right. Maybe the moment's too high. We said P was 31 newtons. Yeah, 7 pounds force. Yeah, that's right. Um, length was, where did we get length? Maybe we used the wrong length. 80 millimeters. That's not going to make a big deal. That doesn't look good. Just change it back here. No, it's not going to be the problem. So what's going on here? We're off by a factor of 3, essentially. The gap is from interference, but the inside burr catches it as it springs up. Okay. So yield's weird. Technically, you're exceeding yield stress, but you might be exceeding it to the point where you're only exceeding it. I mean, you have to follow it along the stress strain curve, and this turns into a nonlinear analysis. And you know, I rarely go that deep. I usually just check to see if it's failing or not. Yeah, this analysis is saying that this is actually yielding a little bit. Maybe that's okay. Um, we could actually solve this to find out what the length has to be based on yield. But yeah, first we need to figure out what's going on here. I mean, is that right? You know what? Let's see. Let's find out if this is actually right. I'm gonna run some FEA on this real quick. I don't know how to solve that in a linear analysis like this. Yeah, it's going to be a tiny, tiny amount, but in the name of making it so that it's reusable for all eternity, I'm just curious to figure out if A, if it really is yielding, and B, well, technically aluminum can't last for eternity because it doesn't have what's it called? Critical I forget what it's called. What is it called? The property of steel that aluminum doesn't have. It doesn't have critical, no, infinite life. Yeah. Aluminum doesn't have infinite life from cyclic loading. Steel does. Aluminum does not. So technically, aluminum would never have been able to do that, but you can get it good enough that it doesn't really matter. Um, that's why planes work despite being made out of mostly aluminum. Save material, aluminium. Leave it up to the reader to know why it doesn't matter that we don't select the alloy. Oh, you know what it is? I bet you there's non-local yielding, elastic yielding in the area around it, which is acting to, yeah, the analysis is conservative. That's what's going on. Yeah, I bet that's it. I bet that's it. So we'll actually do this. So that's force. We don't want force. We want, oh, did we forget to divide the loadout? Duh. We didn't divide the loadout. That's why. Duh, we were off by 4, and it's roughly 4. Yeah, that's why. Okay. So it's P over 4. Remember, because there's 4 of these tabs. See, this is first day stuff. Look at that. You have a 30% overhead. You actually designed this thing perfectly, Jonathan. I would call 1.3 factor safety pretty good. So, yeah. There you go. So yeah, that works. It's exciting. So 30 KSI on 6061 works. Um, aluminum for 5052 has 28 KSI. So interestingly, if you were to use 5052 on this, it would be, what was it, 28? You would be just kissing failure. Shout out Bryce for nailing it. Let's see if you actually have your materials up. Let's see. Materials. 5052 H32. Look at that. So you are yielding technically, but it's a tiny, no, you do have 6061 as well. Okay. And 7075. 7075 especially is going to be plenty scoop up for this. I don't know what temper this is. 60 T6 7075. It's even more skookum than 6061. So you're at, man, they got a lot of values here. 73K SI, which is really cooking. So yeah, you've got more than a 2 to 1 safety factor, which is great. Yeah, so you're fine. Okay, so this is a good baseline um, for us to start building this kind of calculator around. All right, so we've done the calcs. We know this works. So for this fixed tube size, I'm curious if we could, I'm going to get rid of this for now. I'm curious if we could, thanks, Kaya. Appreciate that. So let's actually design something. Like, what does this look like? We know that this is the final state. Like, what if we wanted to go make a frame out of this? Well, let's play around with it. So we want to get this length down, right? What would we have to do to get the length down? So the length is kind of, so actually right off the bat, we have a 2 to 1 safety factor here. We're designing to this number right here. So if we reduce the length, let's do this. We said it's really 75. So we're at two and a half. That's great. So what happens if we reduce? Actually, do we have to rerun all of this? I think we have to rerun all of this. So we have to build this in a way that, all right, well, I'm not gonna do this right now. This will be for the next stream. For now, I just want to get cooking on how to actually like go design something like this. We will design it for this case, which is kind of worst case right now. So let's do this. Let's pull out, yeah, clear the history, and let's see. Well, actually, so this is 2 by 2. I kind of want to give these a different name. The naming scheme I've been using on the repo for the open source stuff was T. So we'll call this the C version of the frame. So we'll just use all the same nomenclature. So this is going to be, so we're going to call this, so T for tube, and then the length. We don't know what the length is yet. It's going to be the C version, and this is revision 0. And then, actually, we'll call this T female, because this receives the male tube. And this will be male. So this will be TM. We don't know the length on that yet. But actually, wait, we could do it so that each tube, yeah, how would this actually work? You could actually put the female on the other side. Or would you have to have female and male tubes? You might have to just have female and male tubes. So just as a start, let's actually mirror this. Yeah, let's actually mirror this. This is a base. So here's our male tube, which makes sense because it has the tabs. And then we have our female tubes. And so let's say we want to build out a simple box frame. So let's do that. So I'm going to kind of go silent here while I start modeling, because I'm not very good at modeling and talking, but I'll try my best. So let's see, we want it to be, what's the dimension from here to here? It is 699 millimeters, so almost a meter. Let's do a meter by meter frame to start. We'll do that. So this is almost, actually we'll do this. Translate this. The start point. Actually, I'm doing this stupidly. Let's do this. Here we go. So make this a meter. It's the thickness. Oh, this is scaled incorrectly. No, it's right. Never mind. Yeah, 50. That's right. So this is going to be 100. So it's going to be 1,000 millimeters to make it a meter, and then it's going to be whatever the thickness was. What is the thickness again? $50.8. So this distance now should be, I did that incorrectly. It's okay, I'll fix it. So now we have a 1 meter-ish frame. How much further off are we? 956.4. Okay, now I'm losing my mind. What's going on? Oh, I was just measuring the wrong. Yeah, okay. So 7.2 millimeters. Now we're a meter. Am I going crazy? Oh, it's the wrong side. Okay. Yeah, I'm going crazy. Okay, that's a meter frame. And so let's make this also a meter. So what are we at right now? 355.6 minus 1,000. So we want this dimension. So we have a meter by roughly a meter frame. First, we have to adjust for the tube length, which is 50.8, I believe. Yep, so we'll move this all over 50.8. It's by 2, 1. Yeah. All right, so now this is meter. We have a meter by meter frame. And so now we want to copy this detail over to this side. How do we do that? I kind of have the minimum dimensions here. I don't think we would ever want to make this any smaller than this. This edge distance from here to here. It's roughly 2.5-ish inches. So yeah, we'll want to leave that the minimum. So what I'll do is I will modify these. Actually, yeah, I'm going to mid-plane these, and we'll mirror this over when we're ready. Okay, and so now we want to, actually we're going to do the same on this side. And I'm going to keep these planes. All right, so these are the centers of my frame, and I'll rework these in a second. So I want to copy this detail into this tube. So it's going to come over here. Okay, so now, can I mirror this all over now? Did I mess up something? I think I'm going to delete something I shouldn't have. All right, so I need to get the mail in here now. How do we do that? Oh, I think I can do this really quickly. Wait, I goofed this. Yeah, okay, I goofed this. All right, so how do I get this imprinted here? Boolean failed. Okay. Okay. That looks right. Um, Okay, so now we need to get this male back over to this side. How do we do that? Let's see if we can find some method to how they constrain this. So they have the gap. It's flush against this side. What about over here? Yeah. Hmm. I think there's a way to just quickly do this. I'll try it out. Okay. Okay. I think this is how this works. So now this became modular, I believe. And I'll mirror it around to see if it's true. This plane. So I'll union these two first. Okay, so here's a 1 meter by 1 meter frame, roughly 3 by 3 feet, if you think in freedom units. And this is now a modular frame assembly based on this mechanism, which is cool. So the idea is you just have well, no, is it one tube? It might be one tube. One tube you can start to build frames out of. I think that's how this works. Right? So this one tube is the same tube for all 4 of these. And now why that matters is because if that's true, that means I can copy this up another 1000 and I can box this sucker out like so. How do I find the center point of this? Just sketch real quick. Okay, and I should be able to now make my box frame like this. If this works, it's gonna be very exciting. Okay, doesn't quite work. What's going on? We're off by just a hair, but that's okay. It doesn't have to be exactly that distance. What is the distance from here to here? It is 812 point some value. No, it's 50.8, duh. So this move over here is wrong. I got to think of the width of the tube. Yeah, so now that works. That is so cool. Okay, but I think the angle changes potentially. All right, well, let's just get it modeled out and we'll start to think about this. And then again, this goes. Yeah, so there's our frame. So you can make this box frame with 6 tubes. No, 1, 6. It's 1, 2, 3. So it's 10, 12 tubes. 1, 2, 3, 4. Actually, I can just do this. This is my favorite way to count in CAD, by the way. You just select the bodies. No, just bodies. 12 bodies. So there you go. You can actually make, with this tab and slot detail, a modular framing system, I think by just having one tube. We ran into a problem here, but I think that's because we just haven't copied the detail over. So actually, let's go back into the history and see if we copy that detail over, does it work out? When I say copy the detail over, I mean if we copy over the geometry of these tab and slot details all around. So let's do that. Here's my center. Snap that here, copy 90. Okay, so how are we going to do this? going to be a little less brutal with this one because I don't want to mess this history up. Yeah, that's right. Okay. Um, wrong way. Okay, so now I should be able to subtract these. And we will get our modular framing system. Wrong way. Okay, let's see if that worked. I think the polarity might be a problem. But we can find a way to center these on the tube so the polarity is not an issue. But I think that works. So we just built a 3 by 3 foot frame with a modular frame system. That is very interesting. These caps kind of suck. We'll have to, because you're going to walk up to and snag one of these caps. That's going to be a real bummer. You're going to destroy the tab and you're going to hurt yourself. So maybe you have to have like little 3D printed caps with these things. But I wouldn't want to do that. Yeah, I wouldn't want to do that. And then what else? You would actually add more to this, I think. Yeah. TBD. Let's so this will be tinyframe dash C00 for now. This is just the concept for this. And we'll commit this to the GitHub so everyone can spin it around and take a look and see what they think. So, yeah. So we'll put this under unreleased. So we're not done with this yet. All right. Cool. Okay. So, take it for a spin. Like I said, I haven't done any interference checks or really anything to see if this actually works 100% yet, but we can do that later. But this is kind of a proof of concept of, hey, actually, you can kind of get in here and just build a simple frame out of this stuff already. I'd be curious to see how much it actually costs to make before we sign off. First, let me make sure that this actually got uploaded. Unreleased, tinyframe C. There you go. So you can download it from here, give that a shot. And then you can also spin the analysis around here. Should open. Yeah. You can actually spin the analysis yourself here in the repo. And then let's do a quick cost check. Let's see. So actually, let me export just this file. What's the length? The length is almost, call that 900. We're going to fix that later. So it's my T-mail, or it's going to be just T900, I think. Let's see. Okay. Let's see what this says. I haven't used FabWorks before. So this is, I think, 2x2 aluminum, 1.6, right? 1.6. Yep. No to burn. 65 bucks. Now I know what you're thinking. That's a lot of money, but what is this? We said 12 pieces, so 12 times $66, so $800. Yeah, that's an expensive frame, but it is reusable. And I think we can make this cheaper. 2x2 is pretty hefty. We're getting there though. That's pretty cool. Yeah. Increase quantity. Oh yeah, you're right. Duh. What was I thinking? Oh baby, look at this. Oh boy. All right. 350 bucks for a totally reusable 3-foot by 3-foot frame. Come on, that's actually not bad. That's pretty great. Yeah. I wonder what happens when you add locating details for the rest of the frame. Like whenever you use Unistrut, one of the upsides is that it includes all of these stamped out slot features, so you can add all kinds of stuff to it. So you have to add that as well to make this really useful. But the upside is that Unistrut is really crappy for dimensional tolerance, essentially, or profile tolerance, technically speaking, around the entire part. This is going to be laser cut, and I think they probably get at least 100, at least 5,000 profile tolerance on that laser. I'm willing to bet. So getting 5,000 over the length of this is crazy accurate. Way more accurate than 8020, I think. Actually, I shouldn't say way more accurate, but the problem with 8020 is that it's an open section, so it is really weak. Whereas per pound, this round tube, I mean this square tubing is way stiffer. But yeah, so if you look up Unistrut, they'll have all kinds of stuff. So they'll have pipe supports and hangers and all kinds of widgets that you can attach to it, and we would do the same here for this. Trolleys, I mean, come on. We're going to build, yeah, I mean, that's great. We're going to build specialized trolleys for this thing. Yeah. All right. Okay, that was fun. It's cool to actually see the analysis be right and be useful. It's actually rarer than you would want. All right, I'm going to continue this, I think, on the next stream. See if we can actually make this into something that we can make. So, all right, thanks for joining, and I will see you next time.